everybody, my name is Josh. I was a computer science examiner for multiple exam boards, head of computer science for UK based schools, and now I run a tutoring business. And these series of lessons is all to give you bite-sized chunks that you can use and still affect your grade, because we've got exams which are coming up on the 10th and the 18th. And people have been asking me to make a networks one. This networks lesson is as much information as I can do. I'm trying to do a video a day so that you've got lots of information that coming up to the weekend you can revise lots for paper one. The way that I think that we can still affect your grade and still maximize the amount of marks, the easiest thing to do is to make sure that your knowledge of all of the different keywords that are coming up in the syllabus. So I've just gone through as many points as possible in the syllabus for AQA and OCR, and also Cambridge International. And the way the marking works, so this is me showing you how it works, is you get a mark for knowledge. Now that's the easiest mark, because it's literally you make a flashcard of all of these different keywords that I'm talking about and you go over them until you can remember them, which if you do that at multiple points in the day, so if you made the flashcards from this, and then what you do is then you practice them a couple of times a day up until the exam, you will remember these definitions. And then let's say that you get a question on peer-to-peer networks and a client-server network, and they're trying to get you to make a recommendation. If you simply just write stuff about the stuff that I'm going to put on here today, so you write stuff about client server and you don't even apply it to the question, so you don't look at anything to do with the scenario and you just write stuff about what a client server relationship is, the likelihood is that you're going to get marks for that. So that's the thing that we can sort of drive home today, that if you can remember to, because I know that time is short now, if you can remember to apply it, so based on the scenario, so it might be a slightly larger company with a bigger budget, then you would make the suggestion that this fits for this company, that it would make sense to use a client server network over a peer-to-peer because they have more money, they can afford to pay for a team of people that are going to look after the network. So it's just, if you can do the extra bit, then you get more marks. But this is the thing that I think we can really do to improve everybody's grades. If you're simply just trying to get an E grade because you keep failing, if you're trying to get a C grade because you keep getting E's and D's, even if you're trying to get the A's and the A stars, the grade boundaries are so low. They're so low on computer science because people just don't do the basics correctly. So let's have a look at all of these different words that I've put up there. I tried to do as many as possible. Okay, so first one was bit rate and baud rate. So bit rate is the number of zeros and ones transmitted in 1 second. Using baseband, this is where the signal is changed 1 bit at a time. Broadband is where you actually transmit more than 1 bit at the same time. So these are just some keywords. So you could get one for baseband, one for broadband, just a flashcard on each of those. Baud rate is the rate at which it changes. And then tying that all together at the bottom, the faster the signal change, the greater the number of bits per second. So that all sounds very confusing. So how's that going? What kind of question are you going to get? The two questions that I see that you're going to get is whether they ask you to work out the bit rate or the baud rate. So it's kind of a little bit like the speed, distance, time triangle, where to work out bit rate, you do baud rate times bits per signal. Baud rate is bit rate, so if we were trying to work out baud rate, I'm just going to bring that one underneath there, so I'm going to divide it, so that's going to give me baud rate is equal to bit rate divided by bits per signal. So we just need to work out what we're actually doing here. Okay, so it's asked us to work out the baud rate, which is going to be so it has a baud rate of 9,600 there, so we've got that, a symbol consisting of 8 bits, the amount of bits per signal. How do you calculate the bit rate in this case? So it's asking us, how do we calculate the bit rate? So what we do is we do 9,600 times 8. So we use this one, 9,600, which is the baud rate, the number of bits per signal, 8, and that gives us this. Okay. If it asks you to work out the baud rate and it gave you the bit rate, you divide the bits per signal by that, and then that gives you the baud rate. So it's just about applying that, putting those different things in there. So that is actually an application question. So if that helps, I thought that was just the different situations you could get on those ones. Describe the structure of the internet. A group of interconnected networks. First part of interconnected, first part of networks, joined it together, it makes internet, because as you can see, network, yeah? The main part of the internet is known as the backbone, second mark there. Each point is connected to other regional networks, usually controlled by internet service providers, ISPs. ISPs are like BT, Virgin, all of these ones. They control access to the end users, us. Keyword, latency. There is going to be a lot of keywords today, people, so flashcard for each of these. Latency is the time delay a communication starts and when it is received at the destination. So it's normally in milliseconds. If you are sending data to the other side of the world, maybe you have family in Australia, it's actually going to take slightly longer because the distance is further. Very, very small, but the latency is increased by distance. So latency is just that the time delay in between sending and receiving. Describe the process of routing. Routers forward data packets from one network to another. So mark number 1. Each router stores data about the available routes, second mark. Each forwarding by router is known as a hop, mark number 3. Routers continue to forward the packets until it reaches its destination, 4 marks. Okay, so that's the process of routing. Again, I'm not going to go too much into the detail of this. It's all about having the biggest impact, which is write this, practice it, and flashcard until it's in your head. Describe what a serial connection is. Sends one bit at a time, one after each other, and this is generally better for long distances. Internet, like what we're using now, will be using a serial connection. Parallel connection is it sends multiple bits at the same time. Very, very fast connection, and it's really good for short distances. So that would be like a printer, internal hardware on the motherboard. It actually uses parallel connections. Over a long distance suffers from something called crosstalk. So a follow-on question, which I didn't write down here, is what are some of the disadvantages? So again, this is just application points. I know that I said I wasn't going to go through too many of these, but it's still worthwhile. If they say to you, like, it's a short distance and they give you a scenario, which one would you pick and why? You'd maybe say, like, if it's a short distance, parallel, could send data very quickly, multiple bits at the same time. It's much faster than serial over a short distance, but over a longer distance, it suffers from something called crosstalk, which is where data interferes with each other and data becomes corrupted because it's all traveling at the same time, and then the data sort of interferes with each other and corrupts the bits. Skew is another bad point, which is where they arrive at slightly different times. So because all of the data is meant to come synchronized, it actually becomes slightly out of order, and then what happens is that then means that you get corruption in the data as well. So there's 2 negative points, hopefully, that you can use in application style questions. Symmetric and asymmetric encryption on this one. So symmetric encryption, this is where you use the same key to encrypt the data and decrypt the data for symmetric, and this is all to do with if you're so the same key is used to encrypt and decrypt. This obviously is a lot less secure, and because it's a lot less secure, what will happen is it's more likely that people could get the data, they could get your key, unlock it, and then they can actually read what's going on there. It's known as a man-in-the-middle attack. Asymmetric encryption is to do with where you have what's called a public and private key, which is used to encrypt and decrypt the data. The private key is never sent over the internet, so what happens is this actually makes the process so much more secure, and again, the application of that is in asymmetric encryption is generally a lot more secure. So if they ask you what's the more secure connection or form of encryption, you would use asymmetric. A firewall is all to do this kind of doing about security. So a firewall has something called stateful inspections, which it checks all receiving and sending packets going in and out of the device, so it's just checking that. Blocks access from certain IP addresses, which is known as a blacklist. It also actually has a whitelist, which allows from certain ones, trusted ones. Blocks access from certain ports. Can be hardware and software. So just in case it asks you a question about how a particular firewall works, and another one, it can be built into a router. Okay, digital signatures, which follows on from the asymmetric and symmetric encryptions. Process to verify a sender's message. So if we need to check whether the person is legitimate, what we would do is we would send a digital signature. What we do is we use the message to actually produce what's called a hash, mark number 3 there. We send the hash over, we encrypt it, then we send the hash over with the, we send the hash over using the private key, and then we send that all over, and then what this will allow the user to do is it can verify that this is the correct person, and then we use the public key to decrypt it. Okay. So yeah, there we go. So that's that one there. This is just a little diagram of it working. So we have a message we're going to send over. The examiners will want to see that you're talking about how the message uses the actual data to create this hash. The hash encrypted is then encrypted and using the sender's private key, creates digital signature. We put that onto our message, and then what happens is we send it over. It's decrypted using the sender's public key, and then the hash value is recalculated, and then they're compared, and then they can see, yep, that is the person that sent it over, and then the match is genuine. So it's that process. If you can bullet point it, just if it asks you to talk about how digital signatures work, that's how that one, how it works on that one. Okay, so again, linked to this is digital certificates. If they just say what is a digital certificate, is where the sender digitally signs a message. They also provide a digital certificate. This is a third party which essentially says that this is a legitimate person. It's known as a certificate authority. The information that could be included on there, so that they may ask you like what kind of things are included on there: a serial number, name of the certificate authority, expiry date, subject public key. It works with computers, but they also actually do it for websites as well. If you go onto Google and then you type it, click up at the top, click on the little padlock on the search bar up at the top of the website, you can actually view the certificate through one of the options there if you wanted to check that out. Now, with this one, with the TCP IP protocol stack, what I want you to do is, so the sort of more A-level questions, I would say, on this one, is where they would actually get you to describe what's going on at each stage. And I'm going to break this down into 2 stages. I want you to get down what the protocols are at particular layers. So here, SMTP, IMAP, POP3, and FTP are all examples of ones that happen at the application layer. There's also HTTP and HTTPS, which is to do with displaying web pages. Okay, if they ask you to simply describe what's going on at, let's say, an application at the application layer, if you remember nothing, just talk about the protocols which are going on there. Just be like, at this stage, this is the SMTP is used to send emails. IMAP is used to receive emails. You'll be able to grab yourself a mark or two, because generally I see people, when I was marking these, people answer these really, really badly. And I'm going to break it down into 2 stages, which is protocols and actually what's going on there. So yeah, to get all those down, they all happen at the application layer. Also HTTP, which is to do with web browsing. HTTPS is just the encrypted one. State 2 protocols at the internet or transport layer. So with the transport layer are these 2 down here, TCP and UDP. Their job is literally just to split the packets up. IP is to do with putting it, which is the internet layer, strangely, is also known as the network layer. So you can use those terms interchangeably, and that's where the IP addresses get put onto them. So the IP protocol. At the link layer, this is the connection. So this is going to be the Ethernet connections, and then Wi-Fi connections as well. Okay, so they're all in there like so. Right. Now, the follow-on question to this is they could just simply ask you for protocols and what's happening with those. They could also say, what is the process of each layer when it's sending data? Okay, and this is the idea behind this. You start at the top, and let's say that I wanted to send an email. It starts there, and then the data is then passed down from the application layer to the transport layer. Okay, so it's, as you can see, like I've put, well, it's got a little arrow on here and it's going downwards. Okay, so it's this idea that the application layer, it picks a protocol, whatever it's doing, so web browsing, encrypting data, that's another thing. It encrypts the data when it's sending stuff, and then it passes it to the transport layer. So the transport layer then receives the data, so you can say that it receives the data from the application layer, and then this is where it splits the data up into packets. You could also talk about how the TCP protocol works on this one, and then it passes it down to the network/internet layer. The network layer then receives the data from the transport layer, and you can see it's this process between going from the top and the bottom. So receives the data, accesses it, and then it will put its protocol on there, puts the IP addresses on where it's going, and then passes it to the link layer. The link layer then receives the data from the network layer or internet layer, puts MAC addresses onto it, and then sends it over the network through either wired or wireless connections. So for the other way around, as you can see, I just actually put in a lovely diagram, which is the arrow going upwards. Groundbreaking, I know, but we also need to talk about how to receive data. So those are the two situations: sending data and receiving data. And if you can get this idea of passing it upwards now, so on the previous one, if we imagine like it starts at the application layer and works its way down when we're sending data, whatever that might be, viewing a website, sending an email, on this side, again, this is where it's all going to be to do with like receiving the data. So it goes the other way. So it starts at the link layer, so it takes the MAC addresses off and then passes the data packets up to the network layer, internet layer if you want to call it that. Takes the IP addresses off at the network layer and then passes the packets up to the transport layer. Transport layer checks for any corrupt packets and reassembles them, then sends to the application layer and checks to see if there's any ones missing. And then the application layer receives the data from the transport layer and then displays the information in the format required, e.g. display email if it was like IMAP or whatever it might be. That's actually a good point, something that I didn't mention. POP3 is IMAP and POP3 are both examples of receiving emails. The thing that you need to know is IMAP keeps it on the web server once you've viewed it, which means that you can view it on multiple devices. POP3 is where you only have to view, you can only view it on one device, which is generally why IMAP is the one which is used now, because we've all got like phones and tablets and laptops and whatever, so we need to be able to view emails on multiple devices. So if we use POP3, that would be a little bit inconvenient. Anyway, so it's this idea. So receiving stuff, it starts at the bottom, works its way up. Sending stuff starts at the top, works its way down. So that is just it. That's the main principle that you can get from that. Then you're going to be getting some marks on that one, and generally people do awfully on that. The benefits of this: each layer is self-contained, each layer is independent of each other and can be compatible with the others. E.g., you change something in the application layer without having to change the other three layers. So that's the main idea of why do we even use the TCP IP protocol stack. You can do stuff at the application layer. I can add a new piece of software at the application layer and it isn't going to greatly affect anything. So that's it means that the other layers are still compatible with each other. Now, other keywords: URL stands for Uniform Resource Locator, a unique address which is used to locate the IP address of a website. DNS, client types into browser. Let me explain this. The DNS is what is the piece of hardware which essentially converts our URLs into IP addresses so that we don't have to remember them. Remembering www.google.co.uk is much easier than remembering an IP address, which we'll talk about in a second. So what the DNS does is it saves us a massive job. Now, as I said, if this is the only thing that you've got, write this down. Or if it talks about the DNS, I will add a little extra point on there as well. But the general principle is you type into the browser your IP, your URL. The URL then gets sent off to the DNS, so it goes off to the DNS. The DNS looks up in a big table the matching IP address to the URL, sends it back to the browser, and then your web browser renders it. Now, sort of a little bit more advanced point it's essentially like what happens if it can't find it at that DNS. So if you want to talk about this, and like little extra is that if it can't find it, then what it does, it goes to the next level of DNS, and then it looks it up there. If it finds it, it sends it back, and make sure you say that in your answer. If not, then it's going to go to the next directory, and it keeps working its way down in the different directories in the DNSs until it finds the URL with the matching IP address. So that's kind of the sort of added part which you may want to put in there. IP address, string of numbers that allow the device to communicate on a network. MAC address, a group of hexadecimal digits which uniquely identifies your device on a network, given by the network interface controller or card. We'll talk more about that in a second. The difference between the two of these, because they kind of sound the same, because both of them are used to identify you on a network. IP addresses are like your house address. If I wanted to send you post, I would address it to where you are, your geographical location. Your IP address changes when you're at school and when you're at home, because you're in a different geographic location. Your MAC address, though, never changes. So like, you don't change, but you might go on holiday and you need some post, so I'll send it to you. So I address that to you, and that's the kind of big difference between the two of them there. You need to know at A level the difference between IPv4 and IPv6. So IPv4 is the old style of IP addresses, which was 2 to the power 32, which is about 4 billion IP addresses. When we first came out with networks, I think it must have been like 80s, 70s. There wasn't that many devices on there. So when they gave like 4 billion different IP addresses, they probably thought, yeah, we're probably good. We don't need to do much else with this, because we're never going to exceed this, because everybody in the world wasn't using computers. It was like, scientific organizations, maybe the military. Then what happened is then, lo and behold, everybody started getting desktop computers, and then now everybody's got a phone and people have got multiple devices. And the world population far exceeds 4 billion IP addresses, 4 billion people. So IP address, we needed to extend it. IPv6 came along, and essentially that, I think it allows for 2 to the power 128. Essentially, the main principle, a lot more, because people have got multiple devices, and there's more than 4 billion people in the world. So that's we needed to counteract that. The NIC, this essentially is the device which allows us to connect to a network. Every single device has this that connects to can connect to a network, and this is what has the MAC address on it. The difference between public and private IP addresses. So it was actually as a method to save some IP addresses, because if you imagine your household probably has, maybe has up loads of devices, smart TV, phones, everybody's got a phone, laptops, whatever, yeah? Let's say 10 conservatively, but it's probably got way more than that. That's 10 IP addresses. So what a router can actually do is, we have the router which has the public IP address, which is where we send all the data to. And then what the router does is it has a table with all of the different IP addresses of what are called the private IP addresses of its own network. So so it would have like a table which has the MAC address with this private IP address. So that we initially send it to your router when we were talking about routing, and then the router then knows, okay, this is going to this MAC address, because the data packet will have the MAC address that it's going to, and then we send it, and then the router's like, okay, I need to send it to here, and that's how it works, and it conserves a lot of IP addresses. So instead of having to have 10, 15, 20 public IP addresses, we just need the one with the router, and then the router can do the bit where it's trying to send over the different data packets to the correct place. Just make that a bit bigger because that's quite small. Okay, so here's some hardware that we've got here. We did sort of do a little bit with the NIC. Wireless access point is wireless transceiver that allows the device to connect to the internet through radio waves. Yeah, so that's normally built into a router. Things on a router, again, this is all just to give you some talking points for them. There are definitely more points on this, but I've just tried to do this as quick as possible for you. Is connects you to the network, forwards data packets to the correct place on devices based on their IP address. We talked about that. Gives devices IP addresses on your network, so that's where it gives you the private IP addresses. You might also say that it's got a firewall in there. You might also say, so you've got that there. So yeah, the other thing is a switch. A switch actually does a lot of the same jobs that a router does, but I have actually seen this question where it says like, what are some of the differences, or what's the similarity and what's the difference between a router and a switch? A switch is when the network becomes larger, your router maybe can't deal with the amount of traffic that's being sent out on the network, and it would benefit from using a switch, because a switch's job just does that. So then the router can connect you to the internet, send the data package to the router, the switch, and then the switch sends them all out. So use that same definition for the router and the switch. I always try and condense things down so that it makes it easier for you on there. Other things that you could also say that it has a table so it has a table of different devices, very, very similar to the router, knows where to send the packets to based on this table. A gateway is something else which is also built into a router, so you've got like the wireless access point and the gateway. And what this does is it allows data that are from different protocols. A protocol is just a set of rules that govern the rules of communication, a set of rules that govern communication on a network. So that tells us how we're going to communicate. And a gateway, say if you've got something coming from wireless networks and you've got something coming from wired networks, the gateway essentially just allows those two to talk to each other. So it's almost like a gateway into two different areas. So that one there, put wired, there we go. And okay, so client server and peer-to-peer networks. What they seem to want to know on this one is like the role of them. So like, what are they doing? So like, what are the different computers doing in each network or style of network? So client server generally it requests computers, the clients request services from the server. The server grants or denies access to these requests. And then you sometimes need to know like some of the different jobs that a server can do. So you've got a web server, which decides what websites you can go onto. If you think about a school, that's the web server is going to be saying like, you can go on this website or not this website. Print server organizes print jobs into a print queue. File server stores files and backs them up. So yeah, you've got some examples there. As I said, there are, I haven't covered absolutely everything, but I'm just trying to get as much information over to you as possible because I do want to do one video a day. Peer-to-peer, all computers have equal status and no computer has control over the network. It's better for smaller organizations with a smaller budget because servers are quite expensive and you normally have to have a team of people that look after it. Advantages and disadvantages. Advantages: handles large amounts of data in comparison to peer-to-peer. Centralized security and updates from the server, so you could just like update all of the computers and then you're good. Better for large organizations with lots of devices that have money to spend. Yeah, you need a team of people to look after it at the server. Peer-to-peer, cheaper as you do not have to spend money on specialized devices such as servers. Easier to manage, do not need to spend money on specialist team. There you go. Better for smaller organizations as well. Yeah, so there's all of that. I think this is specific to AQA. I don't think this one is actually relevant to OCR, but just as a little bonus one is the difference between talking about thin and thick clients. So a thick client is one that doesn't work off I think this is Cambridge International as well, actually. So thick clients, they essentially work by themselves. So they don't need to use a server. So they have the computing power to perform multitasking operations, so like a multitasking OS by themselves. While a thin client is essentially is a computer which is maybe just the bare bones of the computer, but actually all of the processing, so that's the important part, where the processing is done from the server. So I was thinking like maybe a follow-on question if you're AQA or Cambridge International, they may follow that up with talking about thin and thick clients. So just talking about processing done in the computer for thick clients, processing done in the server for thin clients. Okay, structure of a packet and circuit switching and packet switching. What is the structure of a packet? So a packet is just the data that we send over the internet. Splits it up into chunks. That means we can utilize the hardware that's already in place in a computer network. Header, contains the IP address of the sender and receiver, the packet number, time to live limit as well. That's one that I missed off there, but there you go. Payload, the data is the payload. The trailer is error checking methods. Circuit switching. So the difference between circuit switching and packet switching. So circuit switching is where you create a constant communication circuit between one person and another throughout that call or whilst the communication is happening. This is actually how we used to do this is actually how we used to do telephones, and that would be where you would call like an operator, and then some person would like connect you up, and that creates a circuit. That is obviously very, very inefficient, and we had to come up with a new idea for the internet because there's so much data being sent all the time. So packet switching essentially utilizes the hardware already in place, and all of the data packets can take different essentially different circuits because of the different places it can go to. If it asks you a question on this, you just go through the steps. Utilizes the hardware in place. Data splits into packets, all sent and can take different routes where the data is slack, so where there's not as much data being sent, it doesn't get bottlenecked. Get to receiving computer and then reassembled and check for errors, and then it resends any lost errors in there. So that's circuit, packet switching. The differences, we generally, for the internet, we are using packet switching now, so that's the one that we use. Final one, I think this one is only relevant for AQA and Cambridge International, so let me just center this. OCR, this isn't relevant to you. It's the CSMA and CD, carrier sense, multiple axis, and collision detection. So this is an exact exam question which came up. It's just like describe the process of it. What you need to know is this is normally what happens when you've got a bus topology, so like a bus network where you've got multiple people on the same line. It's not like a star net topology, and everybody's sharing the same channel. And this is where what will happen is you're listening to the channel, so that's mark number 1, and only data is sent when free. It's essentially to stop collisions. That's why it's called collision detection at the end there. Because more than one computer is connected to it, can cause a collision, as both may send data at the same time. If a collision happens, what happens is it sends a jamming signal, and then what it does is it waits a random amount of time before it tries to resend the data again, so that you're not constantly getting collisions, which then can cause data corruption and just data not getting to where it needs to go. So that was all of the stuff that I quickly put together for us, so that you've got a networks lesson today, people. I wish you best of luck. Hope that was useful. Take care, and I'll see if I can get something out tomorrow.